Welcome everyone. So in today's class, we will solve some problems and clarify some doubts if you have, and let's see other questions if you can come along. So the first question that we'll solve is we'll establish the relationship between the resistivity and the electric field of free electrons, let's say, or some electron in metals in presence of magnetic field. We are not talking about quantum Hall effect here. We are simply talking about electrons in a magnetic field and electric field, and what is the typical relationship between the electric field and resistivity. Let's say. Later on, we will delve into the quantum Hall effect. Some part of it we already did in class 1, where we are trying to understand that what really happens in presence of high magnetic field for an two-dimensional electron gas, let's say, and we found out that that there are flat Landau levels. So yeah, so we found that the energy of two-dimensional electron gas in a magnetic field is given by this expression, which is again almost same as the harmonic oscillator, apart from the omega b. Omega b is the cyclotron frequency, where omega b in our case is the eb by m, where omega was frequency, or let's say we kind of say frequency in when we talk about the uh, harmonic oscillator in basic quantum mechanics force, which is given by k by m. K is the force constant, where potential energy was given by half kx square, right? So that's the only difference. Otherwise, energy-wise, it was same, and we found out that wave function was like free particle along some direction, and in the opposite direction. So in this case, this is the y direction where the electrons have free particle like behavior, and then the other direction in x direction they are harmonic oscillator wave function consist of Harmonic polynomial and then some exponential term. Gaussian exponential term, right? So, yeah. So that was the so there is square here. So that was the case, and then we saw that Landau levels or the energy levels are quantized in terms of n, which is the energy level index, which are exactly flat. If I plot it with respect to k, the crystal momentum, it has no dependence on the crystal momentum, so it goes exactly flat way, right? And later on we will discover that this flat Landau levels have important consequences in the study of quantum Hall effect and so on. Okay, so let's start today's so the main question is uh, between the electric field and resistivity for 2DG. 2DG is the short form of two-dimensional electron gas in a magnetic field, perpendicular magnetic field. So we'll start from the classical or rather semi-classical understanding, which we often call it Drude model. So in the Drude model, uh, in the Drude model, we have this force equation dV dt, m dV dt equal to the total force, which is minus E and then electric field, and then minus E V cross B, right? This whole part is the Lorentz force due to electric and magnetic field. And then in a solid state system, or let's say metal in general, there are some collision that happens, right? So according to this expression, that as we apply force, then the electron get accelerated and it goes on, right? But that cannot happen in a realistic system. In a metal, we have millions or billions of electrons of the order of 10 to the power 23, and they are randomly colliding with each other as well as with the ions itself. So we consider in the Drude model, we consider that ions are stationary, and then some valence electrons are there, which are kind of free electrons for the metal. So there are continuous spontaneous collision between the electron, and then electron ions as well. The nature of the collision, and then how exactly the collision happens, how is the dependence on the momentum, etc. We ignore all of that, but we phenomenologically introduce that the collision effects tries to minimize, or rather it tries to bring the system in the equilibrium position. And we phenomenologically introduce a new term, mv by tau, which is kind of damping. It is technically actually not damping, but we can think of that there is some scattering happening in the system apart from the Lorentz force that acts on the electrons. So that thing is taken care of by this mv by tau. That tau is the scattering time. And we also assume that let's say here one electron scattered, and here it started after the scattering phenomena, it started its journey, and then another so at this time, so this is, let's say, t0 and then t1, and this time is called tau, equal to t1 minus t0, which is the mean time between the two scattering phenomena. And we assume that between two scattering there is a the electron's path is exactly linear, so there is no curvy path, only just they move in a straight line between the two scattering phenomena. Okay, and then it may again scatter like this one or like this one. There are numerous possibilities, right? And this so the mean time is this tau. Okay, so when we apply electric field and magnetic field, then initially electrons will get accelerated, and then they will also scatter with electrons and ions in the system, and then eventually there will be a equilibrium. So the system will reach an equilibrium position or equilibrium situation where there will be no acceleration in the system. So we can make in equilibrium dv dt will be 0. So there is no acceleration, net acceleration in the on the particles. Okay. So what this gives us is that sorry, minus E electric field minus E v cross b, and then minus mv by, sorry, these are vectors, mv by tau equal to 0, and then v plus e tau by m v cross m. I am just rearranging some terms, e tau by m electric field. So I kept these two terms on the right hand side, sorry, left hand side, and then electric field term on the right hand side. Now the current density in the semi-classical picture or in the Drude model, current density is given by the following formula. So current density J is minus E electronic charge N V. So this is the electronic charge, and then N is the particle density or electron density. electron density, and v is the mean velocity. Okay. Now this velocity and then the current density can have both the components, right? I mean, in general, we are considering, so let's say, let's give this equation as equation 2 and this was equation 1, let's say. So in general, these are matrix element. Why? Because we can have electric field as Ex cap plus y cap, right? So remember, we are in a two-dimensional system. So so if this is the x direction and this is the y direction, then we can have electric field like this at some angle, right? Then we will have ex component and as well as ey component, and we have applied magnetic field along the perpendicular, so it's kind of out of the plane of this board, or let's say this white page. So this is the direction of V. But electric field in principle can have both the components Ex and Ey. Similarly, the current density can also have both the components Jx x cap plus Jy y cap. So these will constitute some I mean, so these will constitute a matrix, right? And the relation between J and E, J equal to something equal to E, let's say, or E equal to something into J. Both are true because we write as current density as sigma matrix, or rather, let's use this third bracket as the matrix notation, and then this is also electric field. Or similarly, we can write electric field equal to matrix of sigma inverse, sigma matrix inverse, and then J, right? And this sigma inverse we call it rho, which is the resistivity. So sigma is the conductivity, and then rho is the resistivity. By the way, just one side note, it's an interesting thing. In Ohm's law, what we read in our elementary courses is that resistance is given by rho L by A, right? And in two-dimensional cases, resistance and resistivity become same. Okay, so the dimensionally they actually become same. So that's another interesting part for 2D. But then let's come back to the initial point where uh, so J is U, so minus E and V. So what we can do is that we'll write this equation 2 and this equation 3 in the matrix form. So writing equation 2 and equation 3 in matrix form, we have so we can have this matrix omega b tau. I will explain how we can get it. uh, Minus omega b tau 1, and this will be j equal to e square n tau by m electric field. Okay. Yeah, so how do we get it? So just replace velocity. So replace velocity expression of equation g, which is velocity equal to, it will be j by minus ne in equation 2. Then what we will get? We are replacing j by ne, and then what was that? This term e tau by m v cross b plus e tau by m v means j by ne cross b, and then there was minus e tau by m electric field, minus e tau by m electric field. So then minus j, or let's say plus j, I multi, so all of these points have one negative, right? So j, and then I also multiply ne on the both side, so e square n tau by m, and then j by ne. Okay, there is also in here, and then n e square tau by m electric field. So if we simplify it again, j plus e tau by m, and then j cross b equal to n e square n tau by m electric field, right? So from this expression, let's say let's call it 4, let's call it 5. So from expression 5, it is very clear that we will directly get equation 4, right? So j cross b will not contribute to the in the direction of b, sorry, j, because j and b, so j cross b direction is perpendicular to j. So the relation between j and e for the diagonal components are simply 1, right? Related by this term e square n tau by m. So as you can see from this term, right, simply the diagonal terms are there related by e square n tau by m, whereas the off diagonal terms are related by omega b tau, where again omega b is equal to e b by m. So again, so see this term, so here one b is there, so e tau m into b, and then j cross b cap, let's say, right? So from this term, these two off diagonal terms are coming. Okay, one is positive, and another is negative, because again, because of the position, j cross b and b cross j are just negative of each other. So from equation 5 you can directly get the equation 4. Okay, so so our question was again, so establish the relationship between the electric field and the resistivity for 2dj in a perpendicular magnetic field. So this expression is itself the so equation 4 is itself the relationship, but we need to express such that electric field equal to something which is, again, we know resistivity matrix, and then j, current density. So what we have, electric field is in terms of, so m by e square n tau, and then that matrix omega b tau minus omega b tau 1, and then j. So this whole term is the resistivity matrix. Okay, So resistivity matrix is for a 2D in presence of magnetic field is given by m by e square n tau 1 omega v tau minus omega v tau 1. So this is our final answer. Okay, so this was one question, and then let's move to the next question. Okay, so before moving to the next question, let's delve some time on the resistivity versus resistance for a two-dimensional case. As I have just mentioned that resistivity and resistance are same, but let's uh, let's show it directly, and yeah, let's show it directly. That will be better. So resistivity we can write in general that resistivity is I'm not giving direct third brackets explicitly, but these are implied that resistivity are matrix and conductivities are also matrix. So resistivity equal to conductivity inverse, which we have rho xx, rho xy, and then minus rho xy, and then rho yy, right? So what we have just saw is that this is equal to m by e square n tau 1 omega b tau minus omega b tau 1. So we can say that this term we can say that this is 1 by omega dc. So it's kind of Drude conductivity 1 omega b tau minus omega b tau 1. So if we want to find out rho xx, what will be rho xx? This term and this term. So rho xx is simply sigma dc inverse. So is the rho yy, right? Whereas rho xy is omega b tau by sigma dc. And so rho xy will be what? Omega b tau, and then omega dc is nothing but the e square n tau over m. So tau tau cancels out, omega b m by e square n. If we write it down, eb by m, which is the equal to omega b, and then m by e square n, it becomes e sorry b by ne, right? So this is what is the Hall resistivity, classical Hall resistivity, right? Where we know that 1 by e ne is the Hall coefficient. In general, we call it Hall coefficient is 1 by q. Q can be the electron or the positive charge, right? Holes basically. But for electrons, this is simply 1 by n. Okay, so this is one nice property that simply from the Drude model we get the Hall resistivity so easily. And then second thing is that how do we measure in experiment? Although in theory we always talk about conductivity, because we calculate current density in we apply electric field or any other field, let's say, and then measure sorry calculate theoretically calculate the current density. And let's say this is the electric field we apply, and then all the coefficient with the electric field we call it conductivity, right? But then experimentalists measure the resistance of a system, so they measure voltage between two ends, and then what is the current sent, so resistance equal to v by I, right? So they measure the voltage and then divide it by the current they have sent in that material, and then they evaluate it as resistivity or resistance rather. So for two-dimensional case, let's show that the Rxy is almost equal to rho xy. Okay, I'm saying almost because these are related by a negative sign, but then essentially that is not the point. The point is that resistance and resistivity are exactly same. Otherwise, for a general case, you know that resistance is rho L by A. Right, A is the cross-sectional area, rho is the current process, and then L is the length of the wire. Let's say I have a cylindrical wire, this is the L, and this cross sectional area is A. So this will be the resistance versus resistivity relationship. But for a 2D system, let's consider material. So again, a 2D system, in y direction the length is L, and we drop a voltage, so Vy in the y direction. So this is Vy in the y direction, and then current is in the, and measure the resulting current in the x direction, let's say. Okay. So we have attached some battery, with through battery we can drop voltage, and then we are measuring that the current through this material is Ix, right? Again, so our emphasis on the Hall conductivity. So we are applying voltage and measuring current perpendicular to the application of voltage direction, right? So then simply we can write Rxy equal to voltage that we have applied along the y direction and the current we are measuring along the x direction. What this will be? This will be L into Ey, and then L into Jx, right? How this becomes? Because due to the voltage application of voltage, so there will be some electric field that will be developed in these 2D materials, and the electric field value is, let's say, Ey. So we know that electric field is just voltage drop by the sample length, right? In more accurate terms, it is dV by dr, let's say, basic electrodynamics course. So this is related by the y direction of length L Ey, E equal to voltage Vy equal to Ey and L, and then current density. In two-dimensional cases, current density means current per unit length, right? In a 3D cases, let's say we have a box, and let's say this is the area in which we are sending some current, right? Here in 3D case, J will be this current density, and current density is the applied current per unit this face area, which is kind of A, let's say. A is maybe L cross L if they are cubic, or this is square shape, right? But for a 2D case, the sample is like only having this area, sorry, this length dimension. So once I send the current, or let's say the current density is developed, then current density means that the current per unit length, this length, right? In 3D case, this was the area, boundary was area, but here the boundary is just a length. So that's why current density is related to the current per unit length in 2D case. So that's why this is Ix equal to Lx and Jx. Okay. Okay. So then this means Ey by Jx and Ey by Jx is related by minus rho xy. Okay. And how do we know this? Again, from this expression, what is that? This expression. Okay. So remember, this was kind of xy notation. So from this expression, what we can get is that ey, the second component, we can write as ex ey here, and then j here we can write as jx, sorry, jy matrix, right? 2 by 1 matrix. So then that will be related as ui equal to minus omega b tau, and then this term uh, m by e square in tau, which is related to jx, and then uh, plus, let's say, if there is some term, I mean m by e square in tau, and then just simply jy. Okay, and what we are trying to find is that uijx because of Hall resistivity. So uijx is simply the minus rho xy, uh, minus rho xy, right? This term, remember, this whole term is rho xy, sorry, rho matrix. So from this expression, yeah, from this expression, let's say rho, so e equal to rho j. From this expression we can say that this is minus rho xy, where we are searching for this term actually here also, right? So this is minus rho xy. So thus it is proved that rxy equal to minus rho xy. Okay. So this is a very nice thing, because what experimentalists measure rho xy and rxy, they don't need to scale with anything. They don't need to measure the sample length and so on to get the resistance or resistivity, right? So what will they measure in experiment? They will directly kind of get from the I mean, whatever Hall resistance they will measure, this is directly or is equal to the Hall resistivity also. But yeah, so this is the nice thing about the Hall part, but this is not the case with the longitudinal part. Okay, for longitudinal part, we have to appropriately divide or multiply by appropriate length. Okay, so next let's move to. So there was one question last time. I answered that question, but there was another way to measure things. So the question was about. So where it goes? Sorry. So how to measure the spin Hall effect? So I am showing from one of the IIT Delhi professors' websites actually. So let's. So this is the spin dynamics lab based at IIT Delhi. So as I said in the first lecture discussion, that in the spin Hall effect, due to the application of electric field, the spins of opposite spins gets collected or gets accumulated at the opposite edges. So this first picture or the first simulation that you see, GIF, let's say, that you see is the spin Hall effect. Opposite spins are, let's say, uh, arranged at the opposite edges of the sample. Now, how do we measure? We measure it by, again, something called inverse spin Hall effect. So this ferromagnet layer is injecting the spin current in the non-magnetic layer, and then this due to this flow of electrons in the non-magnetic layer, so there is a development of uh, voltage, let's say, so which is denoted by EISHE. here in this simulation, or let's say schematic that we see. Then so what really happens is that, so initially we in some material we create spin Hall effect by application of electric current, and then those spin currents are spin pumped. This is called spin pump. From that material which shows that spin current, we pump those spins in another material, and then these spin currents actually creates a voltage difference. So again, so it is essentially we are converting back the spin currents to the charge current, so which we easily can measure, right, just by measuring the voltage. So that's the main idea. Another one is of course the magneto-optical car spectroscopy, but this is one more elegant way that we convert the spin current into the charge current, and we measure the charge current in order to estimate the spin current that was created in the previous material. Okay. So in the last class, we have done Landau level solutions, and we showed the form of the wave function as well as the energy for a free electron gas. But let's see some interesting points about those Landau levels, specifically degeneracy and what is the effect of applying electric field. Because remember, whenever we do experiment, we do apply electric field, right? So electric field is also applied, and then magnetic field is also applied. Then we measure the Hall voltage or longitudinal voltage, whatever. In the last class, when we derived the Landau levels or the effect of magnetic field on free electrons, we have never considered the electric field per se, but this should have been considered. So we will consider that, and before that, whatever result we got, I mean the Landau level in presence of magnetic field, we will see some interesting points about that, especially the degeneracy. Okay. So let me move to this point itself. So we had a Hamiltonian. So this is just small recapitulation. We had a Hamiltonian of 2m minus ea square. Simply that was the Hamiltonian. A is again the vector potential, which is given by this curl of A will give me the magnetic field, and we choose that the Landau gauge or the form of A is simply, sorry, this A is simply Bxy cap, or we don't need to write 0, right? That was our form of Landau gauge, and finally we solved it and have seen that the energy levels are quantized, which are given by h bar omega b n plus half, where n can take 0, 1, 2, 3, etc. And then wave function psi of n k x y, which are spatial position, goes as e to the power I k y. K is the momentum, crystal momentum, or let's say momentum along the y direction, because along the y direction we have seen that the particle remains free, I mean behaves as a free particle, and because of this presence of this x, the translational symmetry along the x direction is lost. That means px Hamiltonian, commutator between px and Hamiltonian is not equal to 0. So the translational symmetry along the x is violated, and we have seen that along the x direction. So by the way, this was Hamiltonian and this is Hermite polynomial. Okay, so this is Hermite. Both are represented by h here, and then h n x plus k l b square. Lb was magnetic length scale, root over h by eb, and then the Gaussian term, minus x plus KLB square whole square, and then divided by 2, sorry, 2LB square. Right? That was our wave function. So immediately we see that the wave function depends on the k along the y direction, momentum along the y direction, but then it has no dependence on the energy. So energy is independent of k. So for all the allowed values of momentum along the y direction, which is represented by k, my energy remains same. That means there is a degeneracy, right? Degeneracy means what? That uh, I change some parameter, but then the energy remains same. So here the degeneracy parameter, let's say we can, if we want to call it, is momentum k. So for all the allowed momentum along the y direction, I have the same energy. So if I have 10 different momentum, accessible momentum, let's say, just for the sake of understanding, then for 10 different momentum, my wave function changes. My wave functions are different, but then energy remains same. So that's creates a degeneracy in the same lambda level. So let's calculate that degeneracy. Okay. And another thing, remember that in the y direction we have a free particle like wave function e to the power I k y, right? So to calculate degeneracy, let's assume that our sample is of dimension Lx along the x direction and then Ly along the y direction. Okay. Now Ly, having a length Ly along the y direction, is like putting a free particle in the box in the y direction of length Ly. So we have done problem of potential well, right? It's kind of like that, because if my sample is restricted to Ly, then the wave function and the particle, especially the particle, cannot go beyond Ly, right? Because out of the sample there cannot be so there can be no electron. We are talking about the electrons of the solid state system of dimension Lx and y, Ly. And so it's kind of potential well of length Ly uh, in the Ly direction. So here potential is 0, and we can think of like as the Ly, so the edge of the sample along y direction comes, the potential suddenly goes like V tending to infinity, right? And for this case, we know that the allowed k is given by 2 pi by Ly, each k, let's say, because what we get actually is that k equal to 2 uh, ny pi by Ly, right? Ny can go to again ny from 0 1 2 etc. If you solve this potential well problem, we will get that. So the momentum is quantized in units of this 2 pi by Ly. And having finite size Lx along the x direction is a little bit more subtle, because in Lx direction or in the x direction, the particles are not really free. Rather, the particles follow the wave function of the harmonic oscillator, right? So some polynomial, harmonic polynomial, and multiplied by the Gaussian function. And these Hermite polynomials, or let's say harmonic wave functions, are centered around x plus KLB square, right? So these polynomials, or let's say harmonic wave function, harmonic wave functions centered around uh, KLB square, right? X plus KLB square. Well, rather, it should be minus, sorry. Uh, Around minus KLB square. So it's being too bad, right? So it's simple to see because minus x square by a square is the our conventional let's say harmonic oscillator wave function. Here the wave functions are centered around 0. We can think of this as a x e to the power minus x minus 0 square by a square, right? So centered around 0 point x equal to 0. Here this is centered around x equal to minus KLB square. So these are localized, exponentially localized rather along the x direction. Now, since I have dimension of x as Lx, system dimension is along the x direction is Lx. So again, the center of the wave function cannot go beyond Lx. So that will be again beyond of the sample. So I have this restriction also, and this restriction gives me that 0 minus KLB square Lx. So this will give me minus Lx by LB square K 0. So this is an interesting point that although K are quantized in units of 2 pi by Ly, let's say, that we have seen here because of the free particle nature along the y direction, but K is extremal values, minimum and then maximum values are limited by the uh, x direction of the sample length as well because of this uh, simple harmonic motions wave function, harmonic wave functions, right? So the degeneracy that we can calculate is that, so basically we want to calculate how many number of states are there with a particular energy E. So the degeneracy n, let's say, is simply Li by 2 pi. This is coming from the k part along y part, and then minus Lx by Lb square, this term. So actually degeneracy, sorry. So degeneracy is simply the summation over dkx dky actually. So then this will be dk and 0. So this limit basically, and this will give me Lx Ly by 2 pi Lb square, which is EB. A is the area of the sample. A equal to Lx and Ly by 2 pi h bar. So degeneracy, we can write more interesting way. EB by A equal to 2 pi h bar means simply h is the Planck's constant, and then B A by h by E, which is phi. Let's say this is the flux and this is the flux quantum. So flux quantum is simply h by E, and then flux through the sample due to the magnetic field is the magnetic field multiplied the area of the sample. So the degeneracy is the how many number of flux quantum is there, right? The flux and divided by the flux quantum. So degeneracy is kind of, we can say that how many number of flux quantum is there in the system. This many degeneracy is there, and for a realistic sample, this number comes out to be very high. I mean, it's of the order of 10 to the power 8, I think. So so in a particular Landau level or at a particular Landau level, so this is our again let me draw the Landau level. Let's say this is the energy versus k. Our Landau levels are exactly flat, right? So this is, let's say, n equal to 0, n equal to 1, and so on. So in each Landau level, there are huge number of degeneracy or degenerate states with the same energy that is there in this Landau level. So there are a lot of electrons that can stay at this n equal to 0, n equal to 2, n equal to 3, etc. state. So later on we will see that how this degeneracy plays a very crucial role in having the quantum Hall states. Okay, so that was one point, and then next we'll move to the turning on an electric field. So far we are considering only the magnetic field, but in experiment we always apply magnetic field as well as electric field. So let's do this problem where we'll simultaneously deal with the electric field as well as the magnetic field. Okay, so effect of electric field on the Landau levels. So again we will use the same Hamiltonian, and the only thing that we will add is that we will assume the electric field is around the x direction. Okay, so our Hamiltonian will be 1 by 2m px square plus py plus ebx square uh, plus ex, because the electric potential will be simply minus ex, right? If I apply electric field along the x direction, and then potential energy is simply minus e phi. Minus is the electronic charge, so that will be e capital E x, that is the potential energy. So again we have used the vector potential of the form 0 vx 0. If you want to check it, if you do curl of it, it will simply be b along z direction. Okay. Okay, so now our task is again, if we can, let's we'll see that if we can convert it to again harmonic oscillator wave function or harmonic oscillator like Hamiltonian, let's say. So this Hamiltonian we just simply explicitly write the square terms, then this will be 2 py ebx and then plus e electric field and x. So notice that there is, so here also a linear in x term, here also a linear in x term. So We need to add them, and then simply we will complete the square term. So this is px square plus py square, and then let's say plus e square b square x square, and then we have py ebx by m, right? 2 cancels out, plus e electric field x. So as a coefficient of x, we have py eb by m plus e electric field. So what we do is that px square plus py square by 2m, and then e square b square x square by 2m plus x, we multiply 1 2, and then e electric field plus e py, I'm just rearranging some terms, by 2, let's say, right? You also need this term in the square as well, as a coefficient of square, right? So to do now, just a second. So I need to complete this square. So we had pyebx, and then electric field x. So what I need to do is that forget about px square plus py square by 2m, and then here was 2m, right? Okay, fine. So one is, so let's consider it e square b square x square by 2m, and then 2, and then I want to bring this term. So what we'll have is that did I mistake somewhere? No, it's okay, I think. So I want to bring these terms. So e b x by root 2 m, let's say, right? And then this term e plus e q y, or rather, let me remove e. So I want to have, I'll take common e b by m, and then x into, so e by mb will be there, or rather this will be me by b. This will be simply py, right? And then divided by 2. That is the case. Yeah, so that is the point. And then what we'll do is that, again, keep aside this px square by 2m, and so again, let's common 1 by 2m py square plus e square b square x square. We'll take 1 by 2m common, so 2 into ebx into me by b plus py, right? So again, px square by 2m plus 1 by 2m. I need, so this ebx is there, but then I need py plus me by b square. So as I took this extra term, I need to mm, extract this me by b square, and also the minus 2 py me by b, right? And then it was as usual e square b square x square plus 2 ebx me by b plus py. This is the term. So again, keep it px square as it is plus 1 by 2m. We are collecting these terms, this term, this term, and this term. Yeah. So py plus me by b square plus e square b square x square plus 2 ebx, and then me by b plus py, right? And then I'm, so minus 1 by 2m of m is me by b square plus 2 py me by b. So me by b. Now what we can write is that px square by 2m plus 1 by 2m into py plus ebx plus me by b uh, square, right? And then the extra terms 1 by 2m m square e square by b square plus 2me by b into py. So this term is again these two terms is again kind of harmonic potential. Just a second, what did it do? Actually, I needed to do something like px square plus py square plus some x minus something square. I need to do this actually. I did something opposite, I think. Yeah, that is where the problem is creating. Okay, so I covered this py whole square, but this is unnecessary actually. Okay, that is the problem. Okay, so I'm mentioning what we need to do very clearly. Okay, okay, so what we need to do is that px square by 2m plus py square by 2m, and then we need to have x square, sorry, rather this will be x minus x0 square into some coefficient. This is again kind of py will be like free particle. Okay, and then px will be dependent on x, so it will not be translationally invariant along x, and then we'll get some extra terms. Okay, actually, so the extra terms will not be associated with any kind of let's say uh, x or y. These will be simply constant. Okay, or so extra terms will be associated only the free particle along ky rather, or py we are writing. So py, e and b extra terms will be only that, so that diagonalization happens very smoothly. So again we'll be able to write, I am just mentioning, I can show that in the next class, because we already spent a lot of time here. So 1 by 2m, and then something x minus x, so sorry, so x minus x0 square, again x0 will be related with will be a function of k, or rather py and electric field and magnetic field. Okay, so with this then there will be some terms, and then p square by 2m plus some extra term that we have set here. And with this we can actually show that electric field, sorry, the energy eigenvalues will be dependent this time on n as well as k. K means we are simply writing py as h bar k. Okay, because there is no k involved along the y direction. Otherwise I can also write ky for clarification, let's say. So nky, the energy eigenvalue will be given by h bar omega b n plus half, and then minus e electric field ky lb square plus e electric field by m omega b square plus m by 2 e square by b square. Okay, so this can be easily provable. I just spend quite time. In the next class I can definitely I'll give you notes. So again, this is like a harmonic oscillator. This is like harmonic oscillator as previously we have seen. And then this is like potential energy, right? So this is minus e electric field and then some length scale ky lb square means length scale. Lb is the length and k is the inverse of length, momentum. So this is length, so it is kind of potential energy. And then this is kind of again kinetic energy, because m by 2 v square, and by the way we know that v is given by e by b, right? So this time the energy versus momentum plot, let's say this is energy n and ky, and this is ky. So they are simply not the flat lands. So let's, if we draw it, the previously these were like that, uh, exactly flat bands, no dispersion along qi, but this time there is a linear dispersion along qi, right? So if this was, let's say, n equal to 0, n equal to 1, n equal to 2, then it will be like this. Okay, so there is linear dispersion along qi. Still they are quantized, but they have a dispersion. And this, because of this dispersion, we get we can we can actually think of that because of application of electric field, uh, the Landau levels becomes dispersive along the ky direction, and consequently we have some current. Other, see, because if we have exactly dispersionless bands, then the velocity is absolutely zero, right? So velocity is given by 1 by h bar del epsilon del ky. Let's say if I want to find velocity along y direction, if it is exactly flat, epsilon is independent of k, I mean there is no dependence of ky, then this derivative is self zero, so there is no velocity of electron. Similarly, Vx can also be zero if it is independent of kx, that we already seen in our gauge choice. But here we will have some velocity, because velocity essentially are the gradient of energy with respect to that momentum along which we are interested in the in finding the velocity. So that is one interesting point which will have later, which we later have important consequences actually. Okay, so let's stop here for today's class. In the next class, we'll solve some assignment problems as well as other problems. Okay. Okay. Thank you for joining.